Hi students, this is Mr. Yang. Today we are going to continue to learn more about vectors. Just like in matrix, right after we learned about introduction to matrix, we have talked about adding matrices and subtracting matrices and multiplying matrices. Same thing with vectors. Today's lesson is going to be about how to add vectors. First, let's review what we have learned in the last lesson. This is a prior knowledge question about component form and magnitude. There's three things I want to emphasize about this question. The first thing is, even though the question says find a magnitude and then write the component vector, my suggestion would always be to write the component vector first and then find a magnitude. That would make things easier. So that's the first thing I want to mention about this question. In that case, let's find a component vector. With the component vector, it's going to be the b minus a. It's going to be the terminal point minus the initial point. So 7 minus -4, -5 minus -3. And this is what I want to emphasize, the second thing. When you're subtracting a negative number, you make sure you subtract a negative number. There will be double negative signs next to each other to make sure you are flipping the signs. And since we have two negative become positive, 7 plus 4 is 11. -5 plus a 3 is going to be a -2. So that is the second thing I want to emphasize on. The last thing I want to emphasize on is when we calculate magnitude. So AB, make sure you use the notation single bar or double bar. We are going to take the square root of both numbers being squared. 11 squared and then -2 squared. When you are squaring a negative number or when you're multiplying with a negative number, you've got to make sure to put parentheses around it. Now that is going to be 121 and that's a 4, so 125. We are going to simplify that radical by making a factor tree. 5 and 25 and then 5 and 5. So basically we have 3 5s. So this is 5 cubed. That means you can take out a pair of 5s and leave a 5 inside. That will be a 5 square root of 5. That is the prior knowledge. Again, the three things I emphasize on: calculate the component form first before you do the magnitude. The second thing, when you're subtracting a negative number, make sure you have the double negative signs. And the last thing is when you are squaring or multiplying by a negative number, make sure that negative number is inside the parentheses. So that is the prior knowledge. Moving on, adding vectors is like following a map. Each vector is a step in the direction of the destination. There are 3 different ways to add vectors, 2 geometrically and 1 algebraically. So basically it's saying, like, let's say this is our starting point. We're trying to get to this destination. We have different ways to go there. We have, several different ways to go there. But that each one could actually be like a vector. So now let's look at the method, the first method, tail to tip. To add vector u and vector v, move v so the initial point or the tail is on the terminal point or the tip of the u. So on the right side in the diagram, you see we start with the u, and the v, let's say the v was here. It's being moved to right next to the u, so it's connected with the tip and the tail. The resultant is from the terminal point to the initial point of v. So, oh, actually, I had it backwards. This is the initial point, and that is the terminal point. So it is from the tail of u to the tip of v, right here to there. The resultant is basically kind of a direct way from where we start and where we end. Basically just focusing on the starting point and the ending point, not quite caring about the process. So that is u plus v. Now let's see how that works in an example. Example 1. My A is right here and it's connected with B already. So I just need to know in the whole process, where did we start? We actually started right here and we are ending right there at the tip of B. So the whole thing, that means this part would be my vector A plus vector B. And make sure you label that as A plus B. Next, example 2. Find the sum of u plus v. This time they're not connected, so we are going to need to move things. As for which one to move, well, u is what we are starting with, so the starting point is going to be the tail of u. So we actually want to move the v. V is basically a diagonal of this one little square, so we are going to move it so it's connected with u, and then it is one diagonal of a little square. That is our v. Next, we can just draw. That's our initial point. That's our ending terminal point. So connect them. This would represent our u plus v. That is example 2. Next, example 3. We have our u and our v. It is asking to find and label the following sum. So for A, we have u right here, and is u plus v. And since we are starting with a u, we are going to keep the u here. We are going to move our v. Our v is basically inside this 1/2 rectangle. So we're going to move it right here so it's connected. And our u is going to be, wait, let me change that. Our u is going to be right here. I mean our v. If that is the case, then we can actually draw. That is our initial point. That's our terminal point. Connect them. That is going to be our u plus v. Next, let's look at our v, because the second part is v plus u. That means we are starting with our v, but we are moving our u. Our u is in a 2/4 rectangle. So we are going to do a 2/4 rectangle right here. And that is going to be our u. In that case, that's our initial point, that's our terminal point. So we are going to connect them to make our v plus u. In this case, we have a question to answer. Is vector addition commutative? That's basically asking, if we're switching their places, are they still going to be the same? And we are trying to decide if they are the same or not. So let me highlight our u plus v and our v plus u. So in that case, that's our u plus v, that's our v plus u. We are trying to decide if they are the same magnitude and is pointing to the same direction. So this is right here, and it is basically let's start with a starting point. Left 3, up 4. Left 3, up 4. In that case, clearly they're pointing the same direction and the same magnitude. So yes, it is commutative because the order doesn't matter. Even though we switch them, we will still end up with the same vector, same thing. So we can basically switch them when we're adding them. That's example 3, which concludes the first method. Now the second method is very similar to the first method, but we are focusing more on forming this shape, which is a parallelogram. If two vector quantities are represented by two adjacent sides of a parallelogram, then the diagonal of the parallelogram will be equal to the sum of the two vectors. So as you may notice, we are basically moving the A, so it's connected with the B. We are moving the B, so it's connected with the A. And then eventually we have this diagonal A plus B. But this overall shape is a parallelogram. So let's have a look at example 4, u plus v. U is right here, so let's do the same thing, move it around. And we will have our u right here. And we can also have our v right here. And in that case, as you can see, we are forming a parallelogram. And that would mean I keep the same starting point for u and v and go to the other point of the diagonal. This would represent my u plus v. That is example 4. Next, example 5. 5.1, that's a component form. Remember, component form always start from the origin. So start from 0, 0. 5.1 is right here. So that is my u. And 2.5 is right here. So that is my v. In that case, I can draw my parallelogram. So up 1 to the right 5. Up 1, 1, 2, 3, 4, 5. This is my u. And up 2, right 2 up 5, that is my v. I can draw my diagonal for the parallelogram right here. So this would be my v plus u. That is example 5. Moving on, example 6. We are doing the same thing as example 5, but afterwards it is asking us to write the resultant vector. So let's draw u first. U is 3, 7, which is right here. That is our u. V is 4, -2. So that is our v. And then we are going to form, you can either do the moving things around or form the parallelogram. That's this method, this example, you can use either method. So we're gonna go right here. That is our V, or you can go there. That is our U. In that case, we have our parallelogram. We can start from that point and go to the diagonal right there. So this is our diagonal, and we can label it as U plus V. And now it's asking for the resultant vector. Let's write it down, U plus V, and we are going to need to write the component form. If you're still confused about how to find the component form, it is quite easy, because no matter what the component form is, we'll always start with a 0, 0, and we basically are identifying where it stops. It is ending at this point, which is 7, 5. So all you need to do is write down the 7, 5, just like it is ordered pair, but then make sure you use the pointy brackets to represent the component form. Next question is kind of something for you to consider. What do you notice about the resultant vector and the given vectors? So you can pause here and kind of have a look at these numbers from U and V and the U plus V. See what you would notice. Hopefully you have had a look and kind of noticed something, but whatever you notice is going to lead us to the last method, which is about the components. The 3 plus 4 is basically the 7. The 7 plus negative 2 is basically the 5. So for component form is going to be quite easy. Method 3. Just like matrix, we were going to be adding matrices element by element or entry by entry. Here for vectors, we are going to add them component by component. So as you can see, the U1 and the V1 are adding together. The U2 and the V2 are adding together. So that is method 3. Now let's have a look at an example. U plus V, that is basically 1 plus negative 1. That's our horizontal components. And 3 plus 5, that is our vertical components. So we are going to get 0, 8. For V plus U, this time the V is in the front, so negative 1 plus 1, and then 5 plus 3. And you may notice we are actually getting the exact same answers. Well, that makes sense, because all we did was just flipping their places. But since addition for vector is commutative, they should actually give us the same answer. And that is example 7. Lastly, we are going to link these with magnitude. So we are going to try to see calculating the magnitude first, then find the sum, comparing to finding the sum first and calculating the magnitude. Are they actually going to be the same, or does the order actually matter when we deal with the magnitude? So let's have a look at example 8. First, for U, the numbers are 6 and negative 9, so square root of 6 squared plus negative 9 squared. Make sure you put negative 9 inside parentheses because it's a negative number. That is 36 plus 81, which is 117. That is not an even number, so when you try to do a factor tree, taking it apart, you can't do a 2, but you can do a 3. If you divide by 3, you got a 39. Then if it breaks down to 3 and 13. That means we have a pair of 3 and 1 13. So we can take out the pair of 3s and leave the 13 inside. 3 square root of 13. Next, the magnitude of vector V, and that is 5 squared plus 4 squared, which is 25 plus 16. So we are going to get a square root of 41. For question C, it is asking us to add the magnitudes together. So 3 square root of 13 plus square root of 41. One thing to mention, you cannot just add the numbers together inside the radical and hoping it's going to be like square root of 54. That does not work. Or some of you may think, well, I can use the 117 add 41, then I got square root of 158. That does not work. The only time you can add these radicals is when they are actually the same and you're like combining like terms. In this case, you can add them together. All you can do is change them into decimals if you want to compare the numbers. So that would be like 17.22. Then if question D is what we just talked about, we are going to add the horizontal component 6 plus 5 and the vertical components negative 9 plus 4. That's going to give us 11 and negative 5. So lastly, for E, we are going to calculate the magnitude 11 squared plus negative 5 squared. Make sure you put -5 inside parentheses. That's 121 plus 25, which is 146. We can try to take it apart as a 2 and a 73, but a 73 cannot go any further. So we are going to stop right there, which is 146 under the square root. If you actually put it in your calculator, that is going to be slightly over 12 something. But clearly, these two numbers are not the same. So here's our conclusion. Calculating the magnitude first, then add, comparing to add first, then calculate the magnitude, they are not going to be the same. Which means when a question is asking you for a magnitude, you can't think, oh, I'm going to add them first. That's going to make things easier. You cannot. They are not the same. However the question is asking you about the magnitudes, you have to calculate it in that order exactly like it's given. That concludes everything about this lesson for adding vectors. Thank you.